Hi everyone. In this video lesson, we're going to do some dynamic analysis of two variable data. So what this means is we're just going to do some like on the fly changes, updates, and see how that affects our model. So that's what we mean by dynamic. So in the past, just very plotting, okay, do this, write your equation, do this, see the correlation. But today we're just going to see what happens as we change our data right away and see the effects in the model in real time. So there's no lesson sheet for today. My hope is that you will use the posted data along with me, and we'll just have a discussion about the results that we see. And the key ideas presented on certain slides in this presentation actually, for the most part, appear on the practice sheet under key concepts. So I haven't posted a lesson sheet, and you can feel free to make notes if you wish, but you don't really have to. So let's get started. We're going to go through two examples today, and here is our first example. In our first example, we're going to kind of revisit the idea of outliers. So here's a table, and I have this in Google Sheets. I'm going to go there in a second. This table shows repair costs over the course of a year for several cars of the same model. And we're going to perform a linear regression, and we're going to see how good the line of best fit is, discuss its goodness. And then we're going to do something new. I'm going to show you guys how to create a residual plot and show how that can be useful to identify outliers. And then we're going to see if we can improve the model in any way. So let's get started. I'm going to head to, here we go. All right, so I have this shared with you guys. It should be shared as lesson 5 data. I believe we're on lesson 5. All right, and yeah, so let's just do our usual. Let's perform a linear regression. Let's see what we get. So we're going to highlight the data in those two columns. Insert a chart. It's nice. Scatter plot right away. It's labeled in this case, which is nice too. Okay, so what we can see is we have this, it looks to be a mostly positive trend, and we got this one guy up here that was a kind of expensive fix. So let's see what kind of model we get. So if your menu drops here, you can just do like chart style or something like that, and then click on a data point, brings up the option for you to add a trend line. We are going to show the R-squared value, and we do want our label to use the equation for this one. All right, so if you look at our line of best fit, notice how it's a bit tilted, right? It doesn't kind of follow the trend. This outlier is kind of pulling it up. And if you look at our R-squared value, 0.08, that's not very good. This model, as it is now, seems pretty weak. Might just type in up here R value. If you do the square root of 0.08, we get about 0.28. So that's not very good. It's a very weak linear model in this case. But that's weird because there seems to be a very strong trend in the graph, except for this guy up here. Now, this guy definitely looks like an outlier. I'm going to show you guys another way that we can detect outliers, and it's called a residual plot. And you guys already know how to calculate residuals, but I'm going to review that with you guys here. So to get the residuals, we need to find out how far each data point is from the line of best fit. To do that, I actually have a column here where we're going to actually get the repair costs that our equation of our line of best fit predicts. And here's how we're going to do that. So in this slot D4 here, I'm going to type in my equation for my line of best fit. 0.0979. Now that's times X. X is our dependent variable. It's the age of the car. So I want to use the value in column B for the age of my car. And I'll do that by doing times. Instead of X, I'm going to write B4. I wanted to use that number in B. And then our model says we add 0.943. And you can see that my equation of best fit says for 4 years, I should get about $1,300. Now, I don't need to just type that in every time. If you Control C copy and then highlight the rest of the unfilled slots and Control V and paste, it updates it for us, which is awesome. And you notice these first three are the same because it's the same for 4 years, 4 years, 4 years. Now we can get the residuals. We get the residuals by taking the data value and subtracting the predicted value, the line of best fit value. So we're going to do equals. I'm going to take the actual value, and in this case, it's C4. I'm going to subtract the predicted cost, which is D4. I get a negative residual of negative 0.73. And again, I can copy that, highlight everything, and paste it down, get all the residuals. So that's really handy. And I want to make a residual plot. So that's going to be graphing these residuals instead of we're going to have age of car on the bottom, but instead of repair costs, I want to have the residual. So here's how we do that. This is a really cool feature. You might probably already know this already, but if I want to make a plot of age of car and residuals, if I hold Control and highlight age of car years and keep holding Control, I can highlight residuals separately. And now I can make a new chart with those two guys. In this case, the default was a column chart. I'm going to change that back to a scatter. And you'll notice for this one, for some reason, we didn't get any titles or anything. So that's okay though. I'm going to just move this guy up for now. Actually, you know what? I'll just put it over top for now. And just, you can, if you want to, this isn't by any means necessary, but I'm just going to do this. I'm going to go to customize and do chart titles and axes. And it's bothering me that we don't have axes there. So I'm going to do under horizontal axis title, we have the age of car. It's like the previous one. And for the vertical axis title, I'm going to put in the residual. Spell it right. And I'm going to give my chart a name. I'm going to call it a residual plot. I mean, not necessary. The residual plot was there anyway, but now we just kind of see what we get here. And so this plots all the residuals. And you can see that we've got more of them below this residual average line of 0. And this one is way, way above. When you have a residual plot and you have one particular data value that's either way above or way below, that's an easy way to identify an outlier. Sometimes easier than just by looking at the original graph. So I think it's safe to say here that that value with the residual of 2, residual value near 2, it was like 1.86, that guy's an outlier. So what happens if we remove that from the model? And here's where the dynamic analysis comes in. So we don't have to redo this problem again. What we can do is we can just take out the value. So we want to take out the value that was really expensive. It was this guy, 432. So I'm just going to delete this row. Actually, I think because I'm going to share this with you guys later, I'm just going to delete the values like that. Then it just stays in there. What you guys will see, which is really cool, and this is the dynamic part, is our line of best fit automatically updated. The equation of our line of best fit automatically updated. And our R squared value automatically updated. And what we can see here is this new R value is the root of 0.937. And we don't even need to do it to know it's very strong positive. 937 about 0.97. So So we've improved the model drastically. We have very strong correlation. We got a nice trend here. Now we do need to update our residual plot. So in the predicted repair costs, this is the old formula. I'm going to update this to have the new formula. So our new formula for our line of best fit is 0.229 times X, our dependent variable, age of car, so times B4. And then we're subtracting 0.126. I do need to recopy that down the rest of my data. That's assuming there's a 0 in there, so I'm just going to delete that one. So I've got my new residuals, and I'm just actually going to make a new residual plot to see what we get. You know what? Do I need to undo? Yeah, kind of updated weird there, but making a new one's not that hard. Hold Control, keep holding, insert, chart, and we'll just make a scatter. All right, that's fine. I think, can I remove this set of values? All right, I'm not going to worry about it. All I wanted was the residual plot, and I've got it down here. The residual plot now, having the residuals versus age of car, is, and you can see each one here. You got about the same amount above, the same below, and that's a sign of a good linear model, is when you drew your residual plot, you have the same number above and below roughly, and you have nothing off to the extremes. And that's what these red dots show here. Let me just quickly see if I can change that chart style setup. X-axis series. Yeah, so here series, I think I can, if I remove this guy, yeah, then I just have the residuals. So I'm not sure why I added that one on. But you can see a much nicer residual plot, no drastic things much farther away than the others, same number above and below. So that's it for this example, guys. We've kind of, you can see the dynamic aspect of this, kind of removing an outlier and seeing how the model updates, but just kind of doing it within some technology and not having to do a lot of handwritten math, just seeing how things change on the fly. So if I go back to our slide here, so the big ideas are the following. So just a formal reminder of what a residual is. It's the difference between the actual dependent value and the value predicted by the line of best fit. And the new plot we learned today is how to draw a residual plot. It shows you how close each data point is to a line of best fit. And an outlier is a point that doesn't fit well in an otherwise linear trend. And often a residual plot is a good way to identify outliers. And something we already know because we did an outlier example earlier, just not one dynamically. An outlier can have a strong impact on a linear regression model if the number of data points is relatively small, which it was in this case because there was only 10 data values. So an outlier is really going to show up. But that same outlier with hundreds or thousands of data values might not affect the model the same way. Removing it might not provide such a big difference. All right, let's go to our second example. And our second example is going to be about hidden variables. So interesting question is absenteeism among professionals on the rise? And here we have data from in our 1990 to, I have it up to 2012 in our spreadsheet. We have data for males and females as well. And this shows the average number of absences for Canadian males and females who have at least one university degree. And we're going to try to determine any trends we can see by doing a dynamic statistical analysis. So let's go for it. So here I have the data already for us. And what we'd like to do, we're going to do two separate graphs here, one for males, one for females, and see if we can see a trend. So let's see if we can see a trend for the males, highlight the data, insert chart. All right, and we got a nicely labeled scatter plot. No need for us to do anything to that. It definitely looks like a increasing trend over time. Let's perform a little regression here to see. Add a trend line, show our squared value, label, use equation. Okay, so R is 0.274, or R squared. So that would mean R is equal to the root of that. About 0.85. So pretty strong correlation. My kids just got home from side turn, so you're going to hear a bit more thumping. So yeah, pretty strong correlation. It looks like the number of abscesses are increasing, and we actually can read off what the average increase per year is a bit. The rate of change here, the slope of this line, is 0.123. So 0.12 absences per year increase for the males. Those are the things we can get just by doing a quick analysis and reading those right off. What about with the females? So I'm going to do the same thing. I'm going to make use of holding control. I think I am. There we go. Control, go down, and hold control. Got the females. Great. And I'm going to insert a chart. And we have the female absences over time. Let me just move my male ones up here. And I'll cut and paste these guys up here just to make some space. All right, and there's the female one. Okay, so interesting graph here. We got a bit of a drop off. It looks like an increase and an increase in two separate spots. So let's see what happens when we do the analysis here. So chart style, click on a data point, trend line, use equation, show R2. Okay, so what we get right now is for R value, 0.188. If we square root that, that's not great. We get about 0.43. And because the line of fit is going down, the R value is negative 0.43. So definitely some weaker, moderate negative correlation going on there. And according to this model, the we got about 0.1 less absences per year for the females. But something doesn't really add up here, right? Because if we look at from around 1997 on, like the trend is increasing, and the trend was increasing before that too. But put together, we get a model where it's decreasing over time. Maybe there's something else going on here. And in fact, there is. So what if I told you we do have something else going on? This excerpt was taken from the data source. So we have a little footnote here. Data before 1996 includes maternity leave. And also men paid using paternity and parental leave are included in the calculation until 2006. So data until 1996 included maternity leave. And so, if we include maternity leave, those women are going to be absent more on average, and the numbers are going to be higher, right? So if we go back to our data, it makes sense that we got a big drop, because if we're not counting maternity leave anymore, then this average is going to drop by a ton. And this big drop corresponds to giving us that negative rate of change every year. So it might be more fair for us if 1996 was when maternity leave was cut out. Maybe we should leave out the data before 1996. And so I'm going to take out these guys here. And See what happens. Yeah, so if you just delete those, we can keep our male graph as it was, and our female just doesn't have anything. And check out the new model. So the new model seems to fit pretty well. It has an increasing trend. Our squared value is much better. If we do the root of 0.67 or 0.615, we get about 0.78. And positive this time because it's going up. And this is definitely more in line with the male model. And here we get about 0.15 more abscesses per year. 0.15 more absences every year, which is now, that's definitely more in line with the males. We have the correlation very similar. Male abscesses going up by 0.12 every year, females going up by 0.15 anymore. There's actually a pretty consistent trend. It's just that the absentee rate in working professionals is increasing every year. And it appears that there's really no difference between the male and female. It might be worth considering and having a look if the if this maternity leave factor was, or paternity leave factor discussed earlier, was a factor with the males. And I think you guys would agree. If you look at the overall trend for the males, we definitely don't have the graph seeming to have two separate trends all on graph. It appears to have this one trend. And I think if we remove the data before 1996, check out how our R squared value changed and how our model changes. So the R squared actually goes down, but we still get about it goes down a bit, but the increase in absences, it's still about 0.1, which is still pretty consistent with what we had earlier. So it looks like this 1996 change in how things were recorded was a hidden variable for the females per year, but doesn't really affect the males per year. So let's have a little talk about this. So the maternity leave being recorded until 1986 is what we call a hidden variable. It's a variable that distorts or obscures the relationship between two other variables. And in this case, it distorted the absentee rate for females. It showed the overall trend is decreasing when actually it was increasing. They can sometimes result in a false correlation or a fragmented trend. We kind of saw that fragmented trend. You're going to see that as almost two trends appearing in the same graph. And it gave us a false correlation. It told us absentees were going down in females when it's actually increasing just like the males. So when you guys are performing analysis, it's important to consider the impact of outliers and hidden variables. So do a residual plot, see if there's outliers. If there's two different trends on the same graph, ask why. Look what happened. Look at the break point of the trend, like in our case, 1986. See if anything kind of happened that would cause that. So consider those when you are conducting a correlational study. So it might help you to remove those to improve the model or account for them when analyzing data. So the next steps for you guys, I have some practice posted. So you will have to enter some of that data manually, but that's not so bad. You guys can do it. I did it, so you guys can suffer a little bit too. But give those a try if you'd like. I do want to share one last thing with you as far as data entry goes, and it might just make your work a bit faster. In a question like this, where you have the data going from 1990 and just increasing by 1 every time, there is a faster way to enter those values. So if you enter 2 to show that you're increasing by 1, this little blue square at the bottom, if you drag it, should show up there. Yeah, if you drag it down, it just increases by 1 for as long as you want. So that works if you have some data that has the same increment every time. It might just save you a bit of time for the data entry. But that's it for me, guys. I hope you have a great day. Stay well, and we'll see you soon.